Hello, and thanks for the nice invitation actually to talk in this workshop. So here what I'm going to talk is about atmospheric neutrinos and the sensitivity that we are going to have with those in the near future. First of all, let me just mention what are the atmospheric neutrinos. So atmospheric neutrinos are created by the collision of the cosmic rays with the atmosphere. Essentially, after that collision, a flux of pions and kaons is produced that they decay into a flux of muon and electron neutrinos, as we can see here in the right plot. We can see actually this flux actually extends from over a wide range of energies going from tens of MeV to order of tens of TeV. From the energies below and above that energy, actually this atmospheric neutrino, the flux of the neutrinos that are reaching those detectors, becomes dominated by astrophysical sources. Now, before reaching the detector, actually, those atmospheric neutrinos, they need to cross the Earth. And the matter effect actually modifies a lot the atmospheric neutrino or the flavor oscillation. This is what we can see here in the right plot, where we have just plot the electron appearance probability, just considering the prime model, the distribution that you can see here in the left plot. As you can see, there are a lot of features that actually depends a lot on those matter effects. For instance, one of them that we can see here is that there is a large resonance for trajectories crossing the mantle of the Earth. That resonance will depend whether the neutrinos are inverted, normal, or inverted ordering, because if they are normal ordering, that resonance will appear in the neutrino channel, whereas if it is inverted, it will appear in the anti-neutrino one. So therefore, actually, using the matter effect, we can just have sensitivity over some parameter that describe the neutrino evolution. Now, this flux actually has been already measured for many years, and for instance, let me mention one of the leading experiments in this sector, which is just Super-Kamiokande. Super-Kamiokande has been measuring this flux for more than 20 years. Essentially, they collect data of events that are contained in the detector, but also they have samples of through-going muons. The latest result of Super-Kamiokande indicates that actually they have a preference for normal ordering of the order of 2 sigma, as we can see here in the right plot, and also a preference for maximal CB violation. But actually, let me tell you that this is not the only experiment that is actually measuring these flags. We also have IceCube. Here, what you have is just the result of IceCube after 8 years of data taking. And first of all, let me mention that IceCube is just a 1 kilometer cube in the Antarctica. In the inner part of the detector, there is a sub-array of photomultiplier that is quite dense, and they are able to measure neutrinos with energy just above tens of GeV. Essentially, they measure the atmospheric mass split in delta M32, for instance, and theta to 3, and the precision that actually they got is quite good, as you can see here. It's on the order of a few 4.3%. And finally, the last experiment that actually is taking data is ORCA. ORCA is still not complete, but actually they just with a few strings they managed to observe an oscillation. Just because so far now they have just a small volume, the precision is not great, but I'm sure in the near future they will collect much more data and the precision will be even better. And here you have one of the results actually in the right plot compared to the other experiment and the oscillation that they have observed in the left plot. Now, what happens, for instance, if we put, let me just put in context those two measurements of atmospheric neutrinos with other measurement coming from long baseline experiment and reactor. Regarding, for instance, the determination of delta M31 and theta 23, we see that actually atmospheric neutrinos provide a very good combination, a very good agreement, sorry, from compared to other experiments. Now, that's interesting because if you combine everything together, and this is what you get here in the color region, the synergies between the different experiments make that actually at the end the allowed region becomes very, very small. And this is what we observe here. Also, let me mention that reactor experiment, they are also able to determine delta m squared 31, and also it is in a very, very good agreement. This is regarding the atmospheric mass splitting, but what about the mass ordering? Well, it's interesting because the combination of IceCube, for the latest result of IceCube with reactor experiment, that boosts the sensitivity or give us a preference for normal ordering of the order of 2 sigma. That is just on one side, but also Super-Kamiokande alone, thanks to this matter effect, they are also, as we have seen before, have a sensitivity on the order of 2 sigma. We combine everything together, what we get is just significance for normal ordering, which is just a little bit above just 2 sigma, 6 units in delta chi square. And finally, the last experiment that the last parameter that actually I would like to mention is the CB violation phase, which is the less constrained one in the three mixing scenario. This parameter actually is quite hard to be measured with atmospheric neutrinos because that flux, as we mentioned before, contains neutrinos and antineutrinos, and actually is quite hard just to separate once they interact in the detector between one and the other. But once we include the information from Super-Kamiokande, we get a preference for a large CB violation in the leptonic sector. Now, this is just the result of the present sensitivity, but what about the future? The first question will be, what experiment are we going to have in the future? And in the future, actually, there are going to be several upgrades of the experiment. For instance, in the future, in a couple of years, we are going to have Hyper-Kamiokande. Hyper-Kamiokande essentially is going to measure the neutrinos produced in an accelerator in Tokai. Currently is running, it's called T2K, so there will be also an upgrade. But together with that one, that experiment, they are also going to collect a lot of atmospheric neutrinos. And here on the right plot, what you have is just some of the event samples that actually that experiment can use in order just to reconstruct the neutrinos. In the left plot, what you have is just the sensitivity that the experiment will have just considering just the beam of the acceleration, atmospheric neutrinos, and the combination of all of them. And it's quite interesting actually to see how the sensitivity can reach values more larger than 7 sigma. So you can see here combining everything together. That's not the only experiment that is working on an update. And for instance, IceCube is currently doing an upgrade. The idea of the upgrade will be just to lower the energy threshold to energy of the order of the GeV scale. And this is important because as we can see here on the right plot, right now with the energy threshold around few order of tens of GeV, it's quite hard, or they are like in the border of exploring the matter effect. And as we mentioned before, the matter effect are important for the determination of some oscillation parameter. What we can understand is that if they manage to lower the energy threshold, this region of matter effect will be fully covered, and that will bring a lot of additional sensitivity to the measurement that they are currently doing. And yes, also let me mention ORCA, because although ORCA is already taking data, what we can expect is that in the near future, they will collect a larger sample of data. So far, in order just to study the sensitivity of ORCA, we developed just a Monte Carlo, based on the reconstruction of the energy and the direction that they have mentioned. And so far, we were considering just neutrinos with energies above 2 GeV, and also consider in our simulation events that can be tracked, cascade, or intermediate. Now, unfortunately, those measurements actually are affected by systematics. Some of them, for instance, are uncertainties related to the flux. The good point here is that the three experiments in some way actually use the same type of flux, although it's not exactly the same because they are located at different locations on the Earth, and therefore the magnetic effect are going to modify the flux at the three different locations. But still, it's going to be quite interesting just to combine the three of them. What are the uncertainties that, for instance, we have over this flux? Here we have just a simplified list of the uncertainty that we have included. And so far we included just uncertainty related to the normalization, the flavor composition of the flux, the neutrino and antineutrino composition, and also the energy dependent and the direction. In the plot, actually, you can see how these flux actually will get modified once those uncertainties are taken into account. Now, those three experiments, what they are using essentially is just water as a target. And what you can see here is just a list of uncertainties that we have considered regarding the scattering of the neutrinos in water. It's quite interesting because, as we were saying before, if you are setting the same target, the combination might help us in order just to reduce the impact of those uncertainties. The only caveat here is that all the three experiments are not working in the same energy region. As you can see here in the plot, Super-Kamiokande and Hyper-K will dominate more the sub-GeV and also the GB region, whereas in the case of the IceCube and ORCA, they will focus more in the GB and the multi-GB region. So therefore, their uncertainties that they are affected is going to be different. Just let me mention that, for instance, for Super-Kamiokande, quasi-elastic and resonant are going to be very important, whereas for instance, for IceCube, it's going to be more the DAS regime, and also for sure in the with the upgrade, the resonance regime. Now, what will happen, for instance, if we combine all of them? So what we have done is just a Monte Carlo for Hyper-K and Super-K. We also made a we used the Monte Carlo provided for the collaboration for IceCube Upgrade. And in the case of ORCA, we also developed our own Monte Carlo where we reproduced their NRA resolution. In the left plot, what you have is just the different event distribution for three different values of the theta to 3. And in the left plot, what you have is just the allow region of each experiment alone and the combination of all of them. As you can see, there is a very good synergy between all of them. And that allows us to reduce a lot the uncertainties. And for instance, that will help us to measure delta M31 with a precision which is below the percent level. Also, excuse me, what you will get is that the wrong octant can be excluded. For sure, that depends on the true value of theta to 3, but in principle can be excluded with a significant larger on the order of 3 sigma. And again, let me just mention that that depends on the true value of theta to 3. In the case that is quite close to maximal mixing, is going to be quite hard. But so far here, what we used was just the value allowed from one of the global analysis. That is here regarding the octant of theta to 3, but what about, for instance, the mass ordering? The mass ordering also, as I was mentioning, is going to modify our event distribution because essentially that resonance that we can see here in this plot can appear in the neutrino or in the antineutrino channel. And that will have an impact in our event distribution, as we can see here in the left plot. That will make, thanks to the large amount of statistics that is collected by those experiments, that we can get a huge sensitivity over that parameter. And this is actually what we can observe in the right plot, where we saw what will be the sensitivity and how the sensitivity will evolve if we combine the three experiments. So far, we were considering that the three IceCube and Super-Kamiokande, the upgrade were starting taking data in 2025. It's not going to be the case, but okay, quite soon. And the main goal or the main idea, the main result in this from this plot, what you can get is that the sensitivity can be can reach values on the order of larger than 5 sigma, just combining the three experiments. The band is just coming from the current uncertainty of theta to 3, that in this case we assume that it's not going to be reduced, but as we have seen in the slide before, actually that is also going to be improved thanks to the measurement of using atmospheric neutrinos. And finally, the CP violation phase. CP violation phase, as we mentioned before, it's not an easy parameter for atmospheric neutrinos because the flux contain both neutrinos and antineutrinos, and it's quite hard just to separate between them. But still, different values of the CP violation will make a difference in the event distribution, as we can see here in the left plot. What you can see in the right plot is just the sensitivity that each experiment will have. The main result is just that Super-Kamiokande and Hyper-Kamiokande they are the leading experiment in the constraining this parameter. The main reason or the main conclusion here is that some part of the parameter space can be excluded just using atmospheric neutrino searches with more than 3 sigma. For sure, long baseline experiment will be better constraining this parameter, but still atmospheric neutrinos can do something, can contribute. And yes, finally, let me mention that actually it's not just atmospheric neutrinos what we are going to do in the future. Actually, there are many other experiments that also are starting to taking data. And actually, just let me mention that Reno present for the first time their first result a few weeks ago. They are very interesting because essentially what they have shown us is that they can measure with an amazing precision the solar parameter. But that's not all, because actually those reactor experiments, Juno, it's measuring the electron survival probability. And what they are essentially doing is just to constrain this delta EE parameter, which is just an effective parameter between or effective combination between the atmospheric mass splitting and the solar one. The precision for this experiment are amazing, and actually they are planning to measure this delta E parameter that is with a sensitivity that is below the percent level, as we can see here in the right plot. And let me mention that in the left plot, what we have is just the first data published by DUNE after 60 days of data taking. Now, this is just regarding the reactor experiment, but atmospheric neutrinos, what they are doing is a different combination, or they are using a different combination in order just to measure the muon disappearance. Essentially, what they have is just a combination of delta N31 and a different one, and a different combination with the solar mass splitting. And this is actually the muon survival probability that you will get. And okay, if you combine both of them, atmospheric measurement and reactor measurement, actually just comparing both parameters delta EE and the delta mu mu, what you will get is also some information, as was explained by Renata, Hiroshi, and Stephen, that you can also get sensitivity over the mass ordering, depending whether this parameter is positive or negative. Just taking the prediction of for the Juno sensitivity after 6 years of data and using the prediction of the determination of delta mu mu from the atmospheric experiment, what I'm showing you here is what we will get if we combine atmospheric and reactor experiment. And we can get that on top of the sensitivity that atmospheric neutrinos will have alone in the determination of the mass ordering, the combination with other experiment like Juno, that will boost, or they will give us an extra 2 sigma, as we can see here, in the determination of the mass ordering. So now let me just conclude saying that actually in the neutrino physics we are entering into the precision era. We still have some uncertainties. For instance, in the 3 neutrino mixing scenario, our largest uncertainties are the mass ordering, the CP violation phase, and the octant of theta to 3. Atmospheric neutrinos can significantly contribute to the resolution of those parameters, in particular the ordering that can be proved with a significance of the order of 6 sigma, also the theta to 3, and for theta to 3 we can reach 3 sigma, and more or less the same for the CP violation, just for some values of the CP violation. What is also quite interesting is that atmospheric neutrinos will be combined with many other experiments, and that combination can help us and boost a lot the sensitivity that we are, or can help us to resolve quite soon many of those uncertainties we have seen in the case of the other order. And that's all. Thank you very much. Thank you.